It'll actually be on the calendar invite. Like once it's finished being created, it'll be put onto the calendar invite. I also usually post it on LinkedIn too.
Okay, awesome.
Yeah. All right, and then I'm just gonna go ahead and get a new session going here. All right. So I'd like everybody to open up RStudio. And just to give people a little bit of background about RStudio, so you have these different components in here. You can create a new file, a new R script. And so we're going to just work in like a plain R script, and we're going to go from scratch and build out our analysis pipeline. I opened up a new R script by clicking this button here and then R script, and you can save that. I'll just put it on my desktop for today, and then I'm going to put it somewhere else later. In this window here, you should have an environment that's empty. This is where any objects that we create are going to go here. You can also explore your files. So wherever there's this thing called a working directory that gets set. So here, actually, this is our working directory right now. And that working directory should be the files that you're navigating. So you can even go in here and like open up files from that working directory. Some of these other things we'll explore a little bit later. The main thing is we're going to be writing our code in here. Okay. So the first thing that we're going to do is we're going to install the Open Specy. If you haven't already installed Open Specy, then go ahead and click Tools, Install Packages, and then type Open Specy. I'm gonna actually reinstall it because I've been playing around. I do a lot of the package development for this, and so there's like a new version that I'm using that I don't want it to be inconsistent with what you're going to be seeing. So once you have the Open Specy package installed down here, you should get a message, package Open Specy unpacked. And that's going to just grab from CRAN, which is like a online repository of our packages. It's going to grab that. And then we're going to type out library Open Specy. Now to run this, so there's a lot of different ways you can run R code. Some people use this other R coding format called R Markdown to do a lot of their coding. I personally don't use that very much. It just adds this whole other layer of complexity for me. So I use pretty vanilla R scripts. But you can either run the current line by clicking this button here, or what I usually do is I do Control Enter. So I just run Control Enter. Once you start running once you read in the Open Specy package, you're gonna get this message that the library is missing or incomplete, and you can run this get lib function to get the Open Specy R package, or sorry, the Open Specy libraries, which are the spectral libraries. And that you should start to see down here in the console, it should start to populate with the package, or the library that it's downloading at this time. If you're running a Mac and you run into any issues with this, let me know. I do have a fix for it. There is one Mac issue that I know is current, or is in the current Open Specy package. All right. So I think I'll assume, feel free at any time if you have any questions or comments. If you want to just like unmute, raise your hand. Let's see. Okay, AI in the chat, or you could post in the chat too. All right, so the first thing that we want to do in Open Specy, so this is for, I'm going to just hash this. So get the libraries, the spectral libraries. That's what that function does. And then first thing that we want to do most of the time is we want to read in some new spectra, right? So there's a bunch of different ways that you can read in new spectra. So the easiest way, or the main way you probably will want to read in new spectra, is to have your own file that you want to grab. Let me see if I can find a good one here. I think that's a. All right, so I have this file called test data CSV. I just navigated to that. If you can also go in here and like, let's say that you wanted to get a file out of here. You could go ahead and click this file. Let's say that that was my spectral file. And I think you can do, let's see, what does it do here? Copy folder path to clipboard. So you'd have this here. And then you can tab. If you tab while you're typing out a file path, it will pop up this search bar that'll allow you to scroll through and be like, oh, okay, I want this one, let's say. I'm going to just use this test data for now. On Windows, this is an issue with the forward slashes, so you have to actually double. What is it? Is this backslash or forward slash? Honestly, I can't remember. This slash, you have to double them for this kind of slash. The other way, you don't have to double them. So if it was this kind of slash, you don't have to double it. But yeah, so to read in this data set, we're going to use the function read in new spectra. Going to use the function read any. And that will read in our test spectrum. Now, if you don't have your own spectrum to work with, I'm going to give you another line of code. So you're gonna actually use some of the onboard test spectra in the package. You're gonna add in another nested function inside of this. So you're gonna add in read ext data file equals and then I think it's Ramen HTTP. Let's see. I hope that works. Let me just double check that. Yeah, okay, that worked. Cool. So these are your two options, right? So you can read in your own spectrum with the read any. You can also read in example data that we have. And you can see the read ext data commands here. Let me see. Do we have all the list of examples in here? I was thinking about this before we started. Yeah. So there's some examples of different like Raman HDPE.csv, Raman academy.spc. There's some different files that we have examples of reading into Open Specy that you can different file names that you can put in there that are different files that you can test out. All right. So read any, this function is supposed to be a very smart function. And you know, the problem with smart functions is that sometimes they're really dumb, and they don't actually work very well. And so what you may, if you encounter any issues with the read any, there's actually a lot of other read functions that are more specific. So like read JDX, read SPC, read SPA. And so you may be able to use one of these for your specific file type. Read any should actually figure out like, oh, this is the issue here. All right. It'll basically figure out like you're trying to read in an SPC or a JDX, and it'll try to read in whatever it is. Okay. So we'll go into different options for visualizing the data. So visualize. And I already kind of showed this one off, but plot and stating the object name should plot your spectrum that you read in. Maybe I can get into what these objects are a little bit, and even what objects are just in general too, actually, for everybody. So in our coding language, you have some different paradigms here. So the first thing is library. So when you read in a library, you're reading in a collection of functions, and sometimes a collection of data sets too. In this case, we have data sets that you're reading in simultaneously. This is called a function. So getlib is a function that just runs a command. It's not necessarily going to put anything into your environment over here. It's not necessarily going to create objects. It can, but a lot of times when you just run a function by itself like this, it's doing an operation, right? So in this case, we wanted to do an operation of getting the spectral library data from a remote repository, and that's what it did. Here, we're using a function, but then we're sending the output over to an object. And so this part, you can name this anything. This could have been test spectra 2. This could have been test spectra win. Doesn't really matter. This part is actually reading the data, and then it outputs data into this new format. So it takes data from a CSV, and it turns it into this here. And this is what we call an Open Specy object. So the Open Specy objects are, I should say, so this arrow pointing here, this is what's saying turn the output into an object named this. That's that part. So the Open Specy objects have 3 different lists items, and a list is a special type of object. The first list item is the wave numbers. So here we can click this, and then it's going to put in some code down here that we can run, and that'll just show us. And I just ran that by clicking enter. That'll show us the wave number values of the spectra, right? Now the second item in the list is called spectra, and that is a collection. It's a data table, so it's like a spreadsheet, and every column is a different spectrum. So you can have like thousands of spectra in one of these Open Specy objects. That's no problem, or you can just do one spectrum at a time. no problem either. So then the third item in the list object is called metadata. And so that one has all of the metadata for the spectra, but each row is a different spectrum. And so it has a different metadata in it. So here in this spectrum's metadata, you have X, Y. So these are coordinates. So in this hyperspectral image that we talked about during some of the previous sessions, you have a coordinate system of like where the spectra are located. So these are the XY coordinates of where they would be located. Since we just have one spectrum, or if you had like a bunch of spectra that didn't have XY, it's going to still give them XY because that'll allow us to project our data into something like an image, even if it doesn't have a coordinate system. You can have any metadata in here. You can put additional metadata in this also. You can put additional metadata inside this metadata list item. And let's say that we want to make sure that the Open Specy object is check object is formatted in a way that's going to work well with the functions that we use. So there are ways you can corrupt these objects, and I'll just show you real quick. So check Open Specy test spectra. This should return true if everything's working well. If the Open Specy object is formatted correctly, this runs through like, I don't know, something like 10 different tests to see like, oh, do we have NA values here? Do the wave numbers have the same length as the spectra? A bunch of different things like that to make sure that like our assumptions when using these functions make sense. Maybe I won't get into like how you can corrupt these because ideally you just don't corrupt them. Ideally, you avoid corrupting them, and that would be the best case scenario. But if you ever do think that you've corrupted your Open Specy object, then go ahead and run this test, the check Open Specy, and hopefully it'll print out a message saying what has been corrupted, and then that'll help you to fix it. As long as you're using the Open Specy, the functions in the Open Specy package, you shouldn't have any issue with corrupting them because we've been really careful to make sure that Open Specy objects always return out the other end as another Open Specy object. All right, so some different ways to visualize the data. So the first one that I showed was just the plot function. This one just produces a plot here. With all functions, you can always you want to know what this check Open Specy function does. Do a question mark and then the function and run that, and that will pop up help. And so this is like one of the really powerful things about our packages and why Open Specy is really powerful, because it's the back end of Open Specy is an R package. It's that you have all this great documentation. So we want to see what this check Open Specy function does, how it behaves, what its commands are. We can see that here. There should be some helpful description in here and down in here that helps us understand what the Open Specy or the check Open Specy function does. And if you ever have any issues with the help not having the information that you're looking for, just email me and I will add it in. All right. Okay, so we got to visualizing the data. So there's another way that you can visualize the data, and it's using a thing called a plotly. So plotly spec, and this one is interactive. So if you want to interact with the spectrum, then you probably want to use that. A lot of times I don't care to interact, and the plot function is like a little bit shorter, so I use that pretty frequently. But in this interactive, it's just like in the Open Specy interface. You can click around, you can zoom in on different peaks, you can download the data as a PNG. Some other nice functions here for like looking at peak locations. For example, you can click this compare data on hover and kind of find, it'll tell you on here what position you're at the bottom. It's hard for me to point at both locations, but at the bottom it says, oh, you're at like 1304. So then right there, 1294 is where that peak is. All right. So that is data visualization. All right. The next thing, I'll pause real quick. Any questions at this point? Okay. Seems like I'm not hearing any. So I'm gonna pre-process the spectra. So this is, we have some spectra uploaded, but now we want to be able to remove the baseline, let's say, or we want to do a derivative transformation, or we want to smooth the spectra. So we've created one function for processing spectra, which is called process spec. And with this function, so we've set all the defaults. Let's go ahead and look at the help for process spec. We have set all of the defaults in process spec to be really similar to the defaults in the Open Specy website. So if you just run process spec on test spectra, and we send that to a new object because we want a new object, processed test spectra. Sometimes they make really long names like that. Process test spectra. So if we just run that all by itself, and then we plot it, that gives us the first derivative, the absolute first derivative transformed spectrum. Now, I'm pretty sure with the plotly, we can overlay them. Spec. Yeah, you have X and then X2. So plotly specs X equals test spectra, and then Y, or sorry, X2 equals processed test spectra. So now we want to overlay them so that we can see the similarities of the raw data and the processed data. And here we can see, okay, it's extracting the peaks where I would expect it to extract the peaks, for example. And it's reducing that baseline. Now, if you wanted to get a little bit deeper into the processed spec function, there's a ton of different commands in here. So we have conform, adjust intensity, conform spec, restrict range, flatten range, subtract baseline, smooth intensity. All these things, these are things that are in the processing tab of the Open Specy interface, right? And so let's say we're like, oh yeah, we don't want to do the derivative transform. We want to do a baseline correction. So now we need to actually start like formatting all of these commands in here. So I'm gonna go no baseline test. I'll just say TS for test spec. Now we're gonna go process spec, and then we're gonna do test spectra again. And I'm gonna paste all of these commands in here. I don't want that last comma in there. That was misspelled. All right. And I'll just run through like what each of these do. So in so active, this is actually something that's, if you turn this to false, it will not process your spectrum. This is really helpful for when you have an interactive workflow where you're kind of like, oh, okay, if this happens, don't process the spectra. You can then just send your logical test over to this function, and then it will basically like fail the process, and it just won't. It'll just keep it raw. So usually if you're processing your spectra, usually you want that to be true. Adjust intensity. Similarly, we have these different tests here. So adjust intensity or restrict range. This is something we built in mainly because the Open Specy website has this as a logic. Like if you click on or off, adjust intensity, then it will turn on and off this part of the command. Now adjust intensity args, that's where you're going to have your different arguments listed for the function. So here we have to put these arguments in a list. So we have list and then type equals none. That's the default. So what does that mean? What's the name arguments? Let's see here. Oh, that one's incorrectly labeled. One sec, let me. I'll show you where the function is that has more just intense. So there's a function, for some reason that one's labeled as in the help as being the smooth intense function, but actually it's this one. So adjust intense, and each of these, like the conform spec, subtract baseline, each of those are a function in Open Specy. So even smooth intense is a function too. So in here, you can set this type argument to none, reflectance, or transmittance. So if you had transmittance data, you'd want to set this to transmittance. If you have reflectance data, you want to set this to reflectance. And that will run the appropriate transformations to get it into absorbance units, which basically like all the other functions are going to be assuming that it's in absorbance units. In some cases, if it's not in absorbance units, then it's going to be really like the function will totally not work. So this is a really important step to do right away. Our data is already in absorbance units, so we don't have to worry about this. Conform spec. So here we have conform spec. Similarly, so this one we have it turned off. This one we have it turned on. And this one, what it's doing is it is setting the step size, the wave number step size, to 5 wave number resolution. using a linear interpolation. And this range equals null. This isn't something that you necessarily need to worry about, but it's just going to use the range from the data. You can also specify other ranges if you wanted to do some cropping. All right, then next we have restrict range. So this one is specifically for cropping ranges. So if you turned this to true, and then you set these ranges here, you could, let's just do this one because this one's pretty easy to see. Let's do max as like 2,000 and then the min as 1,000. So we're basically just doing the fingerprint region here. And I'll just show you plot no baseline. What happened? Oh, I forgot to set this to true. All right, here we go. So now we've cropped the range that we're looking at to just be from 2,000 to 1,000 wave numbers. Usually you want to look at as much data as you can. So we're going to keep that at false. And this is also, I think this is also a nice way to just like be able to turn on and off functions in the code too, because there's all these different, like these functions are kind of nested together. Flatten range. This one is really useful for infrared spectra. If you want to like remove a peak and just make it a flat line from side to side. So let's say like, let me just run this again. Let's say we want to remove this peak from like 1,500 over to 1,400. So here we can set this to true. Sometimes, like maybe that peak's an artifact, for example. That's why we might want to do that. 100. Oops. So you got to set the max to 1,500 and the min to 1,400, and then we can run that. And now that peak has been flattened. It's just a flat line now. Okay, I'm gonna set that one to false again. All right, so now I'm actually getting to the thing that we originally wanted to do. So we wanted to turn off the derivative. So the derivative transformation is happening with this smooth intense function. So we have here this derivative equals 1, absolute value equals 2, window equals 11. This part, we're going to set this to false to remove the derivative transformation. And then we're going to set this subtract baseline function to true to turn on baseline subtraction. So now what we've done, you can see this transformation is quite different from what we were looking at before. And I'm just going to add in this plotly spec here so that we can compare the test spectra to the no baseline. Now you can see what the baseline subtracted spectrum would look like compared to the test spectra. And you can, on this one, you can zoom in and make sure that, that baseline correction is happening well. Let's say here, you're like, oh, okay, I don't really like this tail over here. Well, you can increase the degree of the baseline polynomial to, I don't know, like 15 or something, because this tail, this isn't a real, like this is an artifact of the baseline subtraction, and also this part is an artifact of the baseline subtraction. It's basically not fitting the baseline correctly in those regions, and it's creating these like artificial peaks. So usually increasing the degree of the baseline polynomial will remove those artifacts, and in this case it did. So now we were able to suppress those, and this is a better baseline corrected spectrum. Okay. Hopefully this isn't like too basic for everybody here. Hopefully you're let me know if this is like new stuff or if this is all pretty yeah, new stuff. Okay, cool. If you have any questions, go ahead and just unmute or throw them in the chat too. I know this is a pretty complicated function. We're trying to make it really simple by making it so that like if you don't set some of these commands, for example, it'll give you a relatively good result, like just running it process spec test spectrum. But we do also want, especially with the R package, we really want you to have like a lot of power to be able to fine tune things programmatically. So all right, so we've gone over processing spectra, and if anybody, I'm just gonna copy this whole code and put it in the chat. This way, like if you have gotten lost or something, or there's something not working at this point, you can just run this. Looks like it cropped off part of the. Let me see here. Plotly, where did it crop it off? I think it cropped it here. I'm gonna paste the other part in here now. See, is that it's not allowing me to put everything in the chat at once. That's super annoying. Sorry. Let's see. Okay, so now we're at restrict range. Upload as a text file. Oh, that's a good idea. I'm not sure if I'm not sure that Google allows you to do that though, unfortunately. I don't think they allow you to share files in this. Yeah. Okay. Well, I'll just finish this here. Restrict range. Okay. Where do we get to this? Okay. Polynomial. Smooth intense. True. Okay. We're getting close. Okay, I think I got everything in there. So you just have to copy them through and then paste them all together. But hopefully those will work if you're getting lost at all. All right. So the next thing we want to do, yeah, see a hand raise.
See, sorry, because just wanted to make sure because I did get lost. Where did you get the how do you call this? The parameters, like from where did you just copy and paste them? These parameters from, or I was distracted. Sorry. Oh, okay.
Great question. So, yeah, great question. So what I did question mark and then process spec, and then in here you have all these are the default arguments, and so if you just copy these and then copy and then paste in here, that'll like have you have the default all set, right? And then you can fine tune from the defaults a little bit easier.
Yeah, I got to the part where you were fine tuning, but I didn't know where you got it, and I didn't want to interrupt.
Yeah.
Thank you.
No, thank you. Yeah, please interrupt me at any time. No worries at all. This is what we're here for. So yeah, thank you. Julian?
Yeah, I mean, maybe in the same way I had that question that was hanging over with respect to the degrees of the polynomial. I mean, the default seemed to not be enough. So I wondered, was it a good default? And should we have a default as 15?
Yeah, it's a good question. There's the paper that this function came from, the peer-reviewed study that we like got this function from. It's called the imod polyfit function. They recommended 8. And so that's why that default has been set to 8. But a lot of times I find that the degree should be higher, and that like making the degree higher doesn't really have a lot of downsides, but occasionally it does have a downside. Basically, what it will do occasionally is it will overfit the peaks. And so it kind of depends on how strong your baseline is in your spectrum that you're uploading. If you have a really strong or you have a really weak baseline correction with a high degree of polynomial, it'll start to fit the peaks and remove the peaks. So yeah, there's like a trade-off, and it's not always going to be at 8. That paper kind of thought that was a good compromise, but yeah, I've definitely found sometimes it's better to be a little bit higher.
So 8 would more or less guarantee that you won't overfit and remove the peaks, but in some cases you may still need to tweak. But I mean, what's the trade-off then if you didn't adjust the degree here to 15 and left it at 8? I mean, I assume you'd still get the same matching on the spectrum, maybe not.
Yeah, I mean, those artifacts weren't super strong. I think if let's see. Yeah, this is the last one here. So those artifacts were pretty weak. Like this small peak here, those are some pretty weak baseline artifacts. I bet that this spectrum would identify correctly because the real peaks are much larger than those artifacts.
Yeah.
Yeah, good question.
Thanks.
Thank you. All right. So yeah, for the last thing I wanted to get to, so there's 2 other things I think that I wanted to talk about. I wanted to talk about identification, and then I wanted to talk about where to get more information. I think that was it. And this. Okay, I'm probably not going to get to viewing hyperspectral images. I did want to get to that today, but it's basically the same process. So I'll just start with doing identification here. So the first part with identification is you need to read in a library that's going to be comparable to the way that we process the spectra. So if we want to do the baseline corrected spectrum, then maybe we would use the no baseline library. So we use this function, so lib, and then we go load lib, and then derivative, or not derivative. We want the no baseline. And let's say that we want to identify so this library, this is also an Open Specy object. So that's one question you might have, how can I create my own library? Well, you kind of already did when you uploaded your single spectrum. That could be a library spectra. And there's nothing really that different about these other than that they have a lot more metadata associated with them. And there's specific metadata called, I think sample name is going to be an important metadata for some of the operations for doing identification, but it's not like too crazy to manipulate them to get them to like work really seamlessly as a library. And just using a raw Open Specy object, a different Open Specy object should work. So, all right, so we'll do match spec. And this is the main function for driving identification in the R package. So we'll pull up the help for that. Even though I developed these functions, I still look at the help a lot because I forget there's like hundreds of variables with all of these things, right? So yeah, definitely use the help function often. So in match spec, you have your unknown spectrum. So X equals, we're gonna try to identify the no baseline TS, and then library equals the lib. Now there are some other arguments like conform equals false. So this one actually we're gonna need to this is an important one because if conform equals false, then the no baseline library, if it doesn't have the exact same wave numbers as your library, then it's not going to identify correctly. So what we're going to do here is we're going to set this conform spec equal to false in the no baseline TS first. So that way we're no longer doing that baseline, the confirmation of the wave numbers to every 5 wave numbers, because we want it to be the same as our library. So then here we're going to set conform, back to identification. And then here we're going to set conform equal to true. And so that's going to run that confirmation step, but it'll run it between your spectra and your library. Okay. And then here, so some other options, we have the type equals roll. So this is the type of the way that it's going to get conformed. A rolling confirmation is basically going to take the nearest wave number from one and match it to the nearest wave number in the other. Top n, if you set this to some number, it'll just return the top like 10 matches, let's say, or top 1 match. Order, this is whether you want them to be sorted from greatest to least. Add library metadata, add object metadata. So these, you're going to need to specify the column names of how you match the library and object metadata to the result. And then fill, I don't think you need to worry about that one. That's kind of a more advanced feature. So let's just go ahead and do this match spec. I am going to add in the add library metadata equals, let's see here. Add library metadata equals sample name, because in the library objects, if you're using our library objects, basically the column names in the spectra list object are the same as the values in sample name. And so what this will do is it'll add all that metadata from the library into the result that we get from match spec. Okay, so then we're going to output that into results. And it's going to take a minute to run the analysis. It's basically running a correlation coefficient search between the no baseline spectrum and the library. And then it should give us a new data set of the results. And you have all of your metadata here on the results. You can actually, if you wanted to find the top match, for example, you could just sort and say, oh, okay, here we have library ID, It's a Raman. It's probably a Raman spectrum, an HDPE spectrum. So it was able to find the correct result. That's great. And you have all these other hits. Now, if you had a lot of spectra, that you can, all of these processes, these will work for one spectrum, or you could do them on thousands of spectra all at the same time too. So it's all vectorized in that way. And right now we're just doing one spectrum. If we just wanted to see like the top match, for example, we could have done something a little bit easier and set the top n equals to 1. And now we're just going to get the number 1 correlated match results from the library. So now we have 1. And you get all the metadata for that top match here. So we have Raman, HTTPE again. Okay. So from this now, I mean, this actually, this is really the basics of how to use the Open Specy R package. But I want to share with you if you want to get into some more advanced topics, you have a specific use case. We have way more functions than this, and we even have like experimental functions that we're working on right now, which have really some crazy advanced stuff. But like here, you know, we talk about this is, I'm gonna paste this in the chat. This is a website that you can go to and you can read all about how to use the Open Specy R package. It has a lot of these examples in here too. I think I ran through actually something very similar to the exact examples. And you can see so you have Open Specy. This is like the main website here. There's a package tutorial. So we go into some more details, like step by step on how to use the R package. There's some more advanced things that honestly I don't really have time to go into great depth here. But if you want to go deeper, I highly recommend reading through this tutorial and working through it to learn about some more advanced features that you can use. Also, there are yet more functions that aren't even really described in the tutorial. So if you're like, oh, that's even too easy for me, I'm trying to do something more complicated, you can click this reference and you can read through the different functions that we have. So we have different functions that'll do different operations in the Open Specy R package. Some of them aren't really well documented in the examples because they're kind of niche use cases. Like one of them like deals with NA values in your objects, which is kind of a more advanced problem that you can run into sometimes when things aren't conforming exactly, but you want them to conform pretty well. We have things for different read NV files, read zip folders. In previous sessions we used the run app function. We also have some like split spec function. This is if you have like a collection of 1,000 spectra, but you want them to be individually Open Specy objects instead of one big Open Specy object. You can use this split spec function for doing that. We have different reading and writing Open Specy objects. So you can write an Open Specy object as a CSV file, for example. Yeah. So we have about 4 minutes left. I'll just stop there. I think this is a good stopping point. And if anybody has any questions or anything else they want to talk about, I am thinking about I think that we're getting into like pretty advanced terrain here. And I just want to make sure that like people are getting something out of each session. So I don't want to go super advanced unless there's like a specific interest that the group has of things to get more advanced on. If anybody has any ideas on like really advanced topics they want to do, please let me know, or different, do like a specific training. Otherwise, what I was gonna do is I think I'm just gonna go in like, I'll probably wait like 6 months and then start back up at 0 again and go back up in case people want refreshers. I find a lot of people are just getting into Open Specy occasionally, and they really need like, oh well, how do you do that simple thing again? And so I was thinking about like each year just going through this like 4 months out of the year, and training people from 0 all the way back up to here again. Any thoughts or comments about that? Oh yeah, I'll paste the last part of the code in here. Yeah, right. Yeah, and if it's okay with folks too, I do have your email addresses. I think it's maybe safe to assume that you want to get future future announcements about Open Specy. So I'll just add you all to the email list, in case you want to stay informed. If at any point that gets annoying, just send me an email. Hey, remove me from the email list. I don't want these anymore, or whatever, and I'll take you off that. But that'll be a way to stay up to date in case I do end up doing some more advanced trainings. I'll just send out a blast to everybody. Hey, I'm gonna do this training on this advanced topic. If anybody's interested, feel free to jump in. Thanks a lot for joining today and for being a part of this. These trainings have helped me a lot to improve Open Specy. We've found like different bugs while we've been doing the training, and I've had people ask questions that in ways that I haven't thought about before. And that's been really helpful for me too, because then I'm like, oh, I should improve the app in this way, or I should add these kind of functions. So I have been taking a lot of that into account. Yeah, Marielle?
Oh, just before you close, I have a question that when I was trying out the app, the Open Specy app, and I put some spectra that, I don't know, I think maybe because they were too similar, an error came out, and I just wanted to confirm with you, because the error said features cannot be all true or false, because that would indicate that there are no distinct features. Is it because, honestly, I had spectra, how you say, the same particle, some, not all of them. Some of them I had the same particle three times. I pointed to the same particle, so I don't know if that caused that all look the same or something like that.
If you send me an email with that file and the error message, I'll try to figure out why that's happening. It sounds like something that we might want to fix. So yeah,
okay.
Thank you all for
for
joining. Yeah, I hadn't seen that error message before. Actually, that error message, I know where that error message comes from, but it shouldn't pop up for most data sets that you're gonna upload. So if it is popping up, then there's probably some either an issue with the app or certain way that the data could be formatted differently so that it gets read in correctly.
Yeah, I think, it was the spectra that I told you, that from the Raman, that identifies everything as dyes. So all of them were the same indigo dye. So I stopped trying after I got the error. Yeah, but yeah, I will send you a message. Thank you.
Thank you. Yeah, and I think, I'm not sure. Are you, so for the training later tonight. I'm trying to remember. Is there anybody else? Maybe some other people will be there. I remember last time it was just you, so don't feel like you need to go to the other training too, since you joined in here. We may, if nobody joins into the later one, then we may just skip it.
Yeah, I joined this one because I was not sure if somebody would be in the other one. So
Yeah.
Yeah.
Well, thank you.
thank you so much.
Thanks. All right. Have a great rest of your evening.
Thank you. Bye bye.